What if I told you that NASA has been searching for aliens for decades, but they're doing it completely wrong? While the space agency methodically studies Mars rovers and icy moons like Europa, maverick scientist Avi Loeb is out there recovering metallic droplets from interstellar meteors that show unusual elemental compositions. The contrast is staggering. NASA won't even confirm life exists elsewhere, while Loeb's Galileo Project is actively scanning for alien technology. Two radically different approaches, but only one might actually find what we're looking for. NASA has discovered over 5,000 confirmed exoplanets, many sitting in the habitable zones of their stars. The Perseverance rover found organic molecules in Martian rocks. The James Webb Space Telescope detected water vapor in distant atmospheres. Yet in every press release, every scientific paper, every public statement, NASA scientists use the same carefully chosen phrases: potentially habitable, conditions suitable for life, biosignature candidates. They never say aliens exist. This linguistic dance isn't accidental. NASA operates under intense scrutiny from Congress, which controls their $25 billion annual budget. Every major announcement gets dissected by politicians who view bold claims about extraterrestrial life through the lens of public spending and voter reactions. When NASA scientists present their findings to congressional appropriations committees, they know that speculative language about aliens could trigger budget cuts or program cancellations. The agency learned this lesson during the 1990s when Administrator Dan Goldin's enthusiastic statements about finding life on Mars generated political backlash. His famous declaration that NASA would follow the water became a cautionary tale about managing public expectations. Since then, NASA has adopted what insiders call institutional conservatism, a communication strategy that frames discoveries in terms of possibilities rather than certainties. Internal NASA documents reveal a different story. Scientists working on Mars missions express genuine excitement about methane plumes and seasonal atmospheric changes that suggest active biological processes. Exoplanet researchers calculate statistical probabilities showing that millions of Earth-like worlds exist in our galaxy alone. Astrobiologists design experiments specifically intended to detect living organisms, not just chemical signatures. But these internal discussions never make it into official communications. NASA's Office of Communications reviews every public statement, ensuring that language remains scientifically defensible and politically palatable. Press releases undergo multiple revisions, with lawyers and public affairs specialists removing any phrasing that could be interpreted as definitive claims about alien life. This creates a strange disconnect between NASA's actual research and public perception. The agency spends enormous resources on astrobiology programs, designs life detection instruments for future missions, and actively searches for techno-signatures from advanced civilizations. Yet they consistently present these efforts as explorations of possibilities rather than expectations. The Kepler Space Telescope mission exemplifies this approach. The $600 million project specifically targeted Earth-sized planets in habitable zones, using transit photometry to identify worlds with the right conditions for liquid water. Kepler found thousands of potentially habitable planets, including some with remarkably Earth-like characteristics. Scientists knew they were looking for worlds that could support life, but official announcements consistently described findings as Earth-sized planets in habitable zones, without speculating about actual inhabitants. NASA's cautious language extends to more speculative research areas. The agency funds SETI Institute projects and maintains partnerships with organizations actively searching for alien signals. They support research into extremophile organisms that could survive in harsh extraterrestrial environments. They develop protocols for planetary protection, assuming that contamination between worlds is possible. Yet public communications frame these activities as preparatory research rather than active alien hunting. Congressional testimony reveals the political calculations behind NASA's communication strategy. Agency leaders regularly face questions about spending priorities, with critics arguing that astrobiology programs divert resources from more practical space exploration goals. NASA administrators have learned to present life detection missions as fundamental science rather than alien searches, emphasizing the broader scientific knowledge gained rather than the specific possibility of finding extraterrestrial organisms. This institutional pressure creates a feedback loop. NASA scientists internalize the agency's communication constraints, self-censoring their public statements to avoid controversy. Graduate students and postdocs learn that career advancement depends on publishing papers with appropriately cautious language. The entire culture of NASA astrobiology emphasizes methodical progress over speculative breakthroughs. The strategy has practical benefits. NASA's measured approach maintains credibility with both scientific peers and political oversight bodies. When the agency does announce significant discoveries, the public and media take the findings seriously because NASA has established a reputation for conservative, well-supported claims. This credibility becomes crucial when requesting funding for ambitious future missions like the planned Mars Sample Return Program or next-generation space telescopes designed specifically to detect biosignatures. NASA's communication strategy also protects against the inevitable disappointment when promising discoveries turn out to have mundane explanations. The agency remembers the 1996 controversy over alleged Martian microfossils in meteorite ALH 84001, where initial excitement gave way to scientific skepticism and public cynicism. By maintaining cautious language, NASA avoids raising expectations that later discoveries might not fulfill. The institutional conservatism extends to mission planning and scientific methodology. NASA designs experiments with multiple confirmation steps, requires peer review for all significant findings, and maintains strict protocols for data verification. This systematic approach takes longer than more speculative research methods, but it ensures that any claimed discoveries can withstand intense scientific and political scrutiny. Current NASA missions reflect this methodical philosophy. The Perseverance rover carries instruments designed to detect signs of past microbial life, but mission planners built in multiple analytical steps to confirm any positive results. The upcoming Europa Clipper mission will search for conditions suitable for life in the Moon's subsurface ocean, but instruments are designed to characterize the environment rather than detect living organisms directly. NASA's careful approach creates space for other researchers to take bigger risks. While the agency maintains its official neutrality on alien life, independent scientists can pursue more speculative research without the institutional constraints that bind government agencies. This division of labor allows the scientific community to explore both conservative and radical possibilities simultaneously, maximizing the chances that someone will find the breakthrough that answers humanity's biggest question. The agency's strategic silence on aliens isn't fear or denial. It's calculated patience designed to preserve credibility for the moment when definitive evidence finally emerges. Avi Loeb doesn't wait for committee approvals or peer review panels when he wants to search for alien artifacts. While NASA scientists spend months analyzing microscopic soil samples from Mars, Loeb charters research vessels and heads straight to the Pacific Ocean floor, hunting for debris from what he believes might be humanity's first recovered alien spacecraft. The Harvard astrophysicist represents everything that institutional science isn't. Where NASA employs teams of hundreds working through bureaucratic approval processes, Loeb operates with small, nimble research groups funded by private donors who don't need congressional justification for their investments. Where NASA scientists publish cautiously worded papers about potentially habitable environments, Loeb writes books with titles like Extraterrestrial, the first sign of intelligent life beyond Earth. This wasn't always Loeb's approach. For decades, he built a distinguished career studying black hole formation, the first stars in the universe, and high-energy astrophysics. He published over 800 peer-reviewed papers, advised dozens of PhD students, and served as chairman of Harvard's astronomy department. His theoretical work on gamma-ray bursts and cosmic reionization earned him recognition as one of the world's leading astrophysicists. Then, Oumuamua arrived in 2017, and Loeb's career trajectory shifted dramatically. The first confirmed interstellar visitor to our solar system exhibited properties that challenge conventional explanations. Its elongated shape, highly reflective surface, and puzzling non-gravitational acceleration didn't match typical asteroids or comets. While NASA scientists and mainstream astronomers proposed increasingly complex natural explanations involving hydrogen icebergs and nitrogen sublimation, Loeb suggested a simpler possibility: artificial origin. His hypothesis wasn't casual speculation. Loeb calculated that Oumuamua's unusual acceleration pattern matched what engineers might expect from a light sail, a thin, reflective sheet designed to harness stellar radiation for propulsion. The object's extreme elongation and tumbling motion resembled debris from a larger artificial structure. Its trajectory through the solar system suggested it wasn't bound to any particular star system, consistent with a probe exploring multiple stellar neighborhoods. The academic response was swift and harsh. Colleagues who had respected Loeb's theoretical work dismissed his artificial origin hypothesis as unscientific sensationalism. Conference organizers stopped inviting him to speak at major astronomy meetings. Graduate students began avoiding his research group, fearing that association with the alien guy might damage their career prospects. Mainstream astronomers developed increasingly exotic natural explanations for Oumuamua's properties rather than seriously consider artificial possibilities. They proposed that the object was composed of pure hydrogen ice, despite the fact that such structures couldn't survive interstellar space. They suggested it was a fragment of a nitrogen iceberg from a Pluto-like world, requiring specific formation conditions that seemed statistically implausible. Loeb found these contorted natural explanations more speculative than his straightforward artificial hypothesis. If scientists were willing to invoke exotic materials and unlikely formation mechanisms, why not consider the possibility that advanced civilizations might build interstellar probes? The academic backlash revealed something troubling about institutional science. Researchers who regularly proposed dark matter particles, parallel universes, and 11-dimensional string theories suddenly claimed that alien technology was too speculative to consider seriously. The same scientific community that accepted the possibility of life emerging spontaneously from chemistry rejected the idea that advanced life might build spacecraft. Frustrated by institutional constraints, Loeb sought alternative funding sources. He approached private donors who weren't bound by peer review committees or government oversight. Eugene Zhang, a cryptocurrency entrepreneur, provided initial funding for what became the Galileo Project. Charles Hoskinson, founder of the Cardano blockchain, contributed additional resources. These donors didn't need to justify their investments to congressional appropriations committees or university administrators. The private funding model allowed Loeb to pursue research questions that government agencies couldn't touch. While NASA missions required years of planning and committee approvals, Loeb could pivot quickly when new opportunities emerged. When sensors detected an unusual meteor trajectory near Papua New Guinea, he organized an ocean expedition within months rather than years. Loeb's research methodology maintains the same rigor that characterized his earlier theoretical work. His papers undergo peer review, his data collection follows established protocols, and his statistical analyses meet standard scientific criteria. The difference lies in his willingness to consider hypotheses that mainstream science avoids. The Galileo Project employs sophisticated technology to monitor the skies for unusual objects. High-resolution cameras, advanced algorithms, and machine learning systems track hundreds of thousands of aerial phenomena, searching for movement patterns that don't match known natural or human-made objects. The project collaborates with government agencies when possible, but doesn't depend on their approval or funding. Loeb's expeditionary approach extends beyond theoretical research. His Pacific Ocean mission recovered metallic droplets from the seafloor using military-grade equipment and filtering systems. The recovered materials underwent detailed compositional analysis at Harvard laboratories, with results published in peer-reviewed journals. Whether or not the droplets represent alien technology, the expedition demonstrated that physical investigation of unusual phenomena can yield concrete scientific data. The contrast with NASA's approach highlights different strategies for scientific discovery. NASA's systematic methodology ensures that any claimed discoveries can withstand intense scrutiny, but the process takes decades and requires enormous resources. Loeb's approach sacrifices institutional credibility for speed and flexibility, allowing rapid investigation of transient phenomena that might otherwise go unstudied. Both approaches serve important functions in the search for extraterrestrial intelligence. NASA's methodical programs provide the foundational knowledge about exoplanets, astrobiology, and space environments that makes the search scientifically credible. Loeb's speculative research explores possibilities that institutional science cannot pursue, expanding the range of potential discoveries. The academic criticism of Loeb's work often misses this complementary relationship. Critics argue that his alien hypotheses damage the credibility of serious astrobiology research, but this assumes that all scientific investigation must follow the same conservative approach. Science advances through a diversity of methodologies, including both careful institutional programs and bold individual initiatives. Loeb's independence from institutional constraints creates unique opportunities for discovery. His research programs can pivot quickly in response to new data, pursue high-risk investigations that might fail, and explore hypotheses that peer review committees might reject. These capabilities don't replace systematic institutional research, but they provide a valuable alternative approach to answering fundamental questions about our place in the universe. The Harvard physicist has created a new model for conducting speculative research while maintaining scientific rigor, proving that maverick approaches can complement rather than conflict with institutional science. Kepler 452b sits 1,400 light-years away in the constellation Cygnus, orbiting a sun-like star every 385 days. When NASA announced its discovery in 2015, the planet earned immediate comparisons to Earth. The world receives similar amounts of stellar energy, exists in the habitable zone where liquid water could persist, and circles a star remarkably similar to our own Sun. Scientists nicknamed it Earth's cousin, and some media outlets called it Earth 2.0. Yet NASA's official announcement carefully avoided any speculation about whether the planet actually hosts life. The Kepler Space Telescope discovered Kepler 452b using the transit method, detecting the tiny dimming that occurs when a planet passes in front of its star. The observatory monitored over 150,000 stars simultaneously, measuring brightness changes as small as 0.01%. This technique requires extraordinary precision. Imagine detecting a flea crawling across a car headlight from several miles away. The telescope collected data for 4 years, building statistical confidence that the observed dimming patterns represented actual planetary transits rather than instrumental noise or stellar variability. NASA's planet classification system relies on specific measurable criteria rather than speculation about habitability. Astronomers calculate the habitable zone, often called the Goldilocks zone, by determining the distance range where liquid water could exist on a planet's surface. This calculation depends on the host star's temperature, luminosity, and age. For Kepler 452b, the star is about 1.5 billion years older than our Sun and roughly 20% brighter, placing the planet at the outer edge of the habitable zone where conditions might be warming rather than cooling over time. The planet itself presents intriguing characteristics that NASA describes in purely physical terms. Kepler 452b has a radius about 60% larger than Earth, suggesting it might be a rocky world or a smaller version of Neptune with a thick atmosphere. Its orbital period of 385 days means it receives stellar energy levels similar to Earth. The host star's spectral class, G2, identical to our Sun, indicates that the planet experiences similar radiation wavelengths and intensities. These measurements provide concrete data about the world's physical environment without speculating about biological implications. TRAPPIST-1 represented an even more remarkable discovery when NASA announced 7 Earth-sized planets orbiting the ultra-cool dwarf star in 2017. 3 of these worlds sit squarely in the habitable zone, with surface temperatures that could allow liquid water to exist. The planets orbit so close to their dim red star that their years last between 1.5 and 20 Earth days. Tidal locking means each planet likely shows the same face to its star permanently, creating extreme temperature differences between day and night sides. The TRAPPIST-1 system demonstrates NASA's systematic approach to exoplanet characterization. The initial discovery came from ground-based telescopes operated by the Transiting Planets and Planetesimals Small Telescope Project. NASA's Spitzer Space Telescope provided follow-up observations, precisely measuring the planet's sizes and orbital periods. The Hubble Space Telescope studied the system's atmospheric properties, searching for evidence of hydrogen-dominated atmospheres that would make the worlds inhospitable to life as we know it. Each observation built upon previous data, creating a comprehensive picture of the system's architecture and planetary characteristics. Current technology limits NASA's ability to detect actual signs of life on these distant worlds. The transit method reveals planetary sizes and orbital periods, but atmospheric analysis requires much more sophisticated techniques. Astronomers can study atmospheric composition during transits by analyzing how starlight filters through planetary atmospheres. But this technique works only for specific atmospheric components and requires extremely precise measurements. Detecting biosignatures like oxygen, methane, or water vapor in Earth-sized exoplanet atmospheres pushes current instruments to their absolute limits. The James Webb Space Telescope has begun addressing some of these limitations, though most of its exoplanet observations focus on larger worlds with thicker atmospheres. Webb can detect water vapor, carbon dioxide, and other atmospheric components in hot Jupiter-sized planets, but Earth-sized worlds around Sun-like stars remain challenging targets. The telescope's sensitivity allows detection of atmospheric features that were impossible to observe with previous instruments, But definitive biosignature detection still requires multiple observations and careful analysis to rule out non-biological explanations. NASA's Exoplanet catalog has grown from 0 confirmed worlds in 1995 to over 5,000 today, with thousands more candidates awaiting confirmation. The Kepler mission alone identified over 2,600 confirmed planets and 4,000 additional candidates. This rapid growth provides statistical evidence about planetary populations throughout the galaxy. Astronomers now estimate that virtually every star hosts at least one planet, with Earth-sized worlds in habitable zones occurring around roughly 20% of Sun-like stars. These statistics transform the search for life from speculation about rare phenomena to analysis of common cosmic environments. If Earth-like planets exist around 1 in 5 stars similar to our Sun, and our galaxy contains over 100 billion stars, then millions of potentially habitable worlds exist within the Milky Way alone. NASA's discoveries haven't proven that life exists elsewhere, but they've demonstrated that the basic requirements for life, liquid water, stable temperatures, and rocky surfaces, occur frequently throughout the galaxy. The catalog continues expanding through multiple survey missions. The transiting Exoplanet Survey satellite, launched in 2018, monitors nearly the entire sky for planetary transits around the brightest nearby stars. This mission focuses on finding planets around stars close enough for detailed follow-up study with next-generation telescopes. The survey strategy prioritizes nearby systems where future instruments might actually detect atmospheric biosignatures or other signs of life. NASA's methodical planet hunting creates the foundation for more ambitious life detection missions. The Roman Space Telescope, scheduled for launch in the mid-2020s, will use gravitational microlensing to find Earth-sized planets around distant stars. The proposed Habitable Worlds Observatory would directly image Earth-like exoplanets, analyzing their atmospheric compositions for definitive biosignatures. These future missions depend on the comprehensive exoplanet catalog that current surveys are building. Each newly discovered potentially habitable world expands the targets available for intensive study, bringing science closer to answering whether Earth's biological story represents a cosmic norm or a remarkable exception. Voyager 1 carries a copper record plated in gold, spinning through interstellar space at 38,000 miles per hour. The 12-inch disc contains 115 images, natural sounds from Earth, music from multiple cultures, and spoken greetings in 55 languages. Carl Sagan assembled a team of scientists, artists, and cultural experts to create what they knew might become humanity's longest-lasting artifact. But the record won't reach another star system until approximately 40,000 CE. NASA approved the Golden Record project in just 6 weeks, an impossibly short timeline that forced immediate decisions about representing 4 billion years of Earth's history and the entirety of human civilization. The team faced fundamental questions that had never been addressed by any organization. How do you introduce humanity to unknown intelligences? What sounds, images, and concepts best represent life on Earth? How do you communicate across species barriers that might be far more profound than any linguistic differences between human cultures? The selection committee included Sagan, science writer Ann Druyan, artist John Lomberg, ethnomusicologist Alan Lomax, writer Lewis Thomas, and producer Timothy Ferris. They worked from Sagan's Cornell University laboratory, sifting through thousands of potential recordings and images. The committee operated under strict technical constraints. The record could hold only 90 minutes of audio and 115 photographs encoded as analog signals. Every inclusion required eliminating dozens of alternatives. Linda Salzman Sagan, Carl's first wife, compiled the spoken greetings after contacting United Nations delegates, university language departments, and cultural organizations worldwide. The messages range from formal diplomatic statements to casual hellos. The shortest greeting comes from Mandarin Chinese. Hope everyone's well. We are thinking about you all. Please come here to visit when you have time. The Arabic greeting translates to, greetings to our friends in the stars. May time bring us together. Each language represented required separate recording sessions, often conducted over international phone lines with embassy officials or academic specialists. Music selection proved especially complex because the committee needed to represent global human creativity while avoiding selections that might seem arbitrary or culturally biased to alien listeners. The final playlist spans millennia and continents: a Peruvian wedding song, Azerbaijani bagpipes, Australian Aboriginal chants, classical compositions by Bach and Mozart, American Blues by Blind Willie Johnson, and Chuck Berry's Rock and Roll. Bach's Brandenburg Concerto No. 2 opens the musical sequence, chosen partly because its mathematical structure might be recognizable to scientifically advanced civilizations. The record's images underwent careful curation to avoid content that might confuse or disturb alien recipients. The committee included photographs of human anatomy, showing male and female bodies in scientific detail. They added pictures of human families, children playing, and people eating. Natural scenes show forests, oceans, and wildlife from multiple continents. Technical diagrams illustrate mathematical concepts, atomic structure, and DNA's chemical composition. Urban environments appear alongside rural landscapes, showing humanity's technological development and relationship with natural environments. Encoding the images as audio signals required innovative techniques developed specifically for the Golden Record project. Each photograph was converted into electronic signals that could be stored as sound waves on the record's surface. The playback instructions, etched onto the record's cover, use mathematical symbols and diagrams to explain the decoding process. The instructions assume that any civilization capable of intercepting Voyager would possess advanced electronics and mathematical knowledge sufficient to reconstruct the images. Natural sounds from Earth occupy significant portions of the audio content, including recordings that capture environments that human technologies were just beginning to document systematically. The committee included whale songs recorded by Roger Payne, whose research had recently revealed that humpback whales produce complex, structured vocalizations that travel across ocean basins. Bird songs represent multiple species from different continents. Weather sounds include thunder, rain, and wind. Geological processes appear as earthquake rumbles and volcanic activity. Human activity sounds range from ancient to modern: footsteps, heartbeats, laughter, fire crackling, tools being used, machinery operating. The selection includes a human mother's first words to her newborn child, captured just moments after birth. These intimate recordings contrast sharply with the formal diplomatic greetings, showing both humanity's technological sophistication and biological nature. The committee faced philosophical dilemmas about representing human civilization honestly, while avoiding content that might create negative impressions. They excluded recordings of war, violence, or environmental destruction, despite these phenomena being central to human history. The decision reflected pragmatic concerns about first contact scenarios, but it also created an idealized portrait of Earth that emphasized creativity, cooperation, and natural beauty over conflict and ecological damage. Technical specifications reveal the creator's assumptions about alien capabilities. The record's cover includes detailed playback instructions using universal physical constants like hydrogen atom transitions and mathematical symbols. The instructions explain the proper rotation speed, stylus tracking direction, and signal interpretation methods. This technical complexity suggests the creators expected any recovering civilization to possess sophisticated technology and scientific knowledge comparable to or exceeding human capabilities in the 1970s. Production required coordinating with multiple NASA centers, recording studios, and international organizations while maintaining absolute secrecy about some content selections. The project budget totaled approximately $18,000, covering materials, recording costs, and coordination expenses. RCA Records pressed the masters using techniques developed for high-fidelity audio reproduction. Each record underwent quality testing to ensure signal integrity during decades or centuries of interstellar travel. The Golden Record project reveals NASA's implicit acknowledgement that extraterrestrial civilizations likely exist and might eventually encounter human artifacts. While the agency maintained official neutrality about alien life in public statements, the Record project required extensive planning for interspecies communication scenarios. The investment in creating humanity's cosmic introduction demonstrates institutional confidence that such contact scenarios warranted serious preparation. The record continues traveling through space, currently beyond the influence of solar wind and magnetic fields. Its trajectory will carry it within 1.6 light-years of the star Gliese 445 in approximately 40,000 years, though the probability of actual discovery remains infinitesimally small. The Golden Record represents humanity's most deliberate attempt at cosmic communication, encoding our species' hope that intelligence and creativity might provide common ground for understanding across the vast differences that separate worlds. On January 8, 2014, sensors detected a meteor entering Earth's atmosphere near Papua New Guinea, with characteristics that defied conventional classification. The object traveled at 37 miles per second, faster than 95% of meteors in NASA's catalog. Its trajectory suggested an origin outside our solar system, making it potentially the first interstellar meteor ever recorded. Government sensors tracked the fireball as it exploded over the Pacific Ocean, depositing debris across the seafloor 50 miles north of Manus Island. Avi Loeb saw an opportunity that institutional science would never pursue. While NASA scientists analyzed the sensor data and published papers about the meteor's unusual properties, Loeb began planning a physical recovery mission to the crash site. The Harvard astrophysicist secured private funding from entrepreneur Charles Hoskinson and assembled a team of engineers, oceanographers, and materials scientists. Their goal was ambitious beyond anything government agencies would attempt: recover microscopic debris from an interstellar visitor scattered across miles of Pacific.